Hello, and welcome to this TI Precision Lab on designing a front-end circuit for driving a differential input analog to digital converter, or ADC. In this video, we will compare a solution using two op-amps with one that uses a fully differential amplifier, or FDA. We will use the knowledge learned from past fully differential amplifier and operational amplifier Precision Labs videos and apply them to this real-world example of selecting the best configuration for driving the ADC. If you have not done so already, please review the following Precision Labs videos in TI content. Many theories, calculations, and simulations used in this video are based on this content and will not be discussed in detail but rather reviewed. Topics covered in this video include fully differential amplifiers, or FDAs, noise, stability, THD, and settling time. Many systems utilize a precision differential input, ADC, as they can provide 2 times the dynamic range, superior common mode noise rejection, and improved signal-to-noise ratio, or SNR. However, oftentimes, the source signal is single-ended. In order to drive the differential input ADC, we need to select an ADC driver that can convert the single-ended input signal to a differential signal. In this video, we will discuss 2 common methods used to perform this single-ended to differential signal conversion, and discuss which method is best for this application. This video will use TI's fully differential input SAR ADC, the ADS8910B, as an example. Before we discuss the 2 methods, let's first understand the input signal source and the ADS8910B. In this example, the input signal source is a single-ended signal, has a 2-volt peak-to-peak amplitude, and a frequency of 500 kHz. The ADS8910B is a differential input SAR ADC and can support a full-scale input range of -Vref to positive Vref with a maximum supply voltage of 5 volts. This means that the input of the ADC can sample signals from 0 volts to +5 volts on either input, allowing the full dynamic range to be 10 volts. For assurance that we will not hit the rails of the ADC, we want the 1 volt input signal to swing from -4.6 volts to +4.6 volts, giving a full dynamic range of 9.2 volts. This means that the ADC driver will need to have the ability to amplify the input signal at a gain of 4.6 and run on a supply voltage of 5.2 volts. The Nyquist bandwidth of the ADC is half of the sampling rate. The ADS8910B sampling rate is 1 megasample per second. Thus, the driver will need to support a bandwidth greater than 500 kHz. The ADC has a -110 dB of THD at 100 kHz. The driver should have better distortion performance so that the driver does not degrade the total THD performance. At an 18-bit resolution, with a full dynamic range of the ADC at 10 volts, the least significant bit, or LSB, of the ADS8910B is about 38.14 microvolts, so low noise will be required to maintain the output signal integrity. And finally, the goal is to minimize power consumption for the system. Searching through TI's available devices, there are 2 amplifiers that meet the criteria as discussed, the OPA625 and the THS4551. They both offer a supply voltage of more than 5 volts, have high bandwidth values, offer low voltage noise performance, have equal or better THD performance compared to the ADC, and have low quiescent current for low power consumption. The OPA625 is a single-ended output operational amplifier, and by utilizing 2 of these amplifiers, we can configure them to convert a single-ended signal to a differential signal. The THS4551 is a fully differential amplifier that can not only do differential to differential signal conversion, but can support single-ended to differential conversion. We will explore which configuration offers the best performance for the precision ADC through theory, calculation, and simulation in noise, stability, THD, and settling time. But first we must select the resistor values for each configuration. For the discrete solution, we need to utilize 2 amplifiers which will have different resistor values. In the first amplifier, our input voltage is 2 volts peak to peak. Our desired output voltage is 4.6 volts peak to peak. Thus we will need a gain of -2.3 volts per volt. By setting RF1 to 246 ohms and RG1 to 107 ohms, our desired gain of minus 2.3 will be achieved. However, the input of the ADC can only see a positive voltage of 0 to 5 volts. Because of this limitation, we need to shift our output voltage by the term V-shift. In this example, shifting our output voltage by 2.5 volts will allow our output to swing from 0.2 volts to 4.8 volts. We can shift our output voltage by connecting the ADC's voltage reference to the non-inverting side of each amplifier, and then use a voltage divider. At the non-inverting input, the gain is seen as non-inverting and is 3.3 volts per volt. To shift our output by 2.5 volts, we need to add a voltage divider at the non-inverting side of the amplifier to out 0.7575 volts, because 0.7575 multiplied by the gain of 3.3 will give us an output voltage value of 2.5. We see that the best resistor combination is 191 ohms and 1070 ohms. For the second amplifier, a gain of minus 1 volt per volt is needed to change the polarity of the signal. Setting RF and RG to the same value as each other will give us a gain of minus 1, and our output will see a voltage of 0 volts to minus 5 volts. As stated before, the inputs of our SAR ADC need this voltage to be 0 volts to 5 volts. We must also shift the output voltage of this amplifier by a total of 5 volts. The non-inverting side of the op-amp sees a non-inverting gain, which, for our second amplifier, will be 2 volts per volt. As long as the resistor values in the resistor divider are equal to one another, the reference voltage will be halved. Our voltage reference value in this example is 5 volts, and thus a resistor value of 470 ohms is used for all resistors. FTAs are a little simpler for this application. FTAs have a VOCM pin that is set to a gain of 1 volt per volt. We simply connect the voltage reference pin from the ADC to the VOCM pin of the FTA. If we set the voltage reference to 2.5 volts, then our output will shift by 2.5 volts. In an FTA, as long as RG and RF resistor values match each other on both the inverting and non-inverting sides of the FTA, it will see an inverting gain. With the resistor values of 493 ohms and 107 ohms, the THS4551 will have a gain of minus 4.6 volts per volt. Using the Analog Engineer's calculator, which is free to download using the link below, we set the charge bucket resistor and capacitor, or R-filt and C-filt, to 690 picofarads and 16.25 ohms on either side. If you want to know the math behind selecting these components, please see the link below to watch the math behind RC component selection. For selecting the best R-filt and C-filt combination, please see or find the R-filt and C-filt values Precision Labs video. Now we are ready to analyze each configuration for noise, stability, THD, and settling times. Noise can be defined as an unwanted signal that combines with the desired signal to result in an error. This can usually be seen as an error in the measured output. Here we will look at the intrinsic noise that is typically generated by the circuit components. The main contributing factors are the amplifier's internal voltage noise, internal current noise, and the components around the amplifier such as resistors. Again, this video will focus on the results. For more information on how to calculate and simulate noise, please see the TI Precision Labs op-amp series for detailed steps. 1/F noise calculations can be complicated. One way to avoid these calculations is to look at the noise corner of the spectral density curve. The noise corner is the point which the 1/F noise and the broadband noise intersect. This can be graphically estimated by looking at the bend in the curve. If the noise bandwidth of the amplifier is 10 times greater than the noise corner, then the 1/F noise can be neglected. In this example, the noise bandwidth is 22 MHz. The noise corner of the THS4551 is around 300 Hz, and the OPA625 is 400 Hz, thus we can ignore 1/F noise. We will not go into detail on the noise calculations for either configuration, since these are covered in previous TI Precision Labs videos. However, the math has been provided for review if needed. For the discrete noise calculation, we need to look at the two amplifiers separately. For amplifier 1, the total spectral noise density is multiplied by 2, as we see this noise in the first stage and the second stage. The spectral noise seen in the first stage is independent of the second stage. The total output spectral noise density caused by amplifier 1 is 21 nanovolts per square root hertz. For amplifier 2 in our discrete solution, by following a similar process as the first amplifier, we get a total spectral noise density of 22.5 nanovolts per root hertz. Combining the spectral noise densities of both stages, and then converting to the total RMS noise, we see that in the discrete solution, we get a total output voltage noise of 106 microvolts RMS. To confirm this, we simulate this configuration in Tina TI. You can perform a noise analysis by selecting Analysis, Noise Analysis, and then plot a graph from 1 Hz to 1 GHz for total noise. Once the plot appears, look at the noise value on where the curve flattens out at higher frequencies. Through the simulation, we get 104 microvolts RMS compared to our calculated result of 106 microvolts. However, this noise is quite high. A big contributing factor to this noise value is the resistors we have on the non-inverting side of the amplifiers. A trick we can use to minimize that noise is adding a 1 microfarad capacitor after the voltage dividers on both amplifiers. This addition basically negates the noise of those resistors. If the math is repeated without the voltage divider resistors, and if we simulate the same circuit, but this time with the additional capacitor in Tina, we see that we have reduced the noise down to 87 microvolts RMS. For the FDA, we calculate noise in a similar fashion to the discrete noise calculation. Please note that this configuration is neither a first order nor a second order system, so a value of 1.365 was used for the brick wall correlation factor. Through calculation, we see that the total RMS voltage noise on the output of the FDA is 92 microvolts RMS. We can simulate this configuration in Tina TI to confirm this value. Again, you can perform a noise analysis by selecting Analysis, Noise Analysis, and then plot a graph from 1 Hz to 1 GHz for total noise. Looking where the noise value on the curve flattens out at higher frequencies, we get a similar value to our calculation of 92 microvolts RMS. In summary, we can see that the FDA and the discrete solution with the added capacitor produce similar noise levels. A downside to adding in these capacitors is that it will require more components to the circuit, and the start time might be delayed as the capacitors need time to charge. Overall, our goal was to make the noise less than 1 LSB. Our noise was a bit higher than that, but this is not uncommon in high-gain applications. For optimal stability, we use a rule of thumb which states that a phase margin of 45 degrees or higher is required. While a circuit may work with a phase margin of less than 45 degrees, it is considered to only be marginally stable and will show significant overshoot and ringing. For more information on amplifier stability theory, stability simulations, and how to make a circuit stable, please see TI Precision Labs on op-amp stability section, which is linked below. Once you have your circuit created in Tina and the feedback loop broken, we can test for an amplifier stability by going to Analysis, AC Analysis, and then selecting AC transfer characteristics. This can be done for both the discrete solution and the fully differential amplifier solution. For the discrete solution, we must test the stability of each amplifier separately. For the first amplifier, we break the feedback loop and see what the phase margin is where the AOL beta curve, or loop gain, crosses the 0 dB region. With a phase margin of about 52 degrees, we can confirm that the first amplifier is stable. Now we break the feedback loop for the second amplifier and see what the phase margin is when the loop gain curve crosses the 0 dB region. At a phase margin of about 39 degrees, we can confirm that the second amplifier is only marginally stable with the potential to become unstable. This second amplifier might need to see additional changes to the circuit in order to stabilize it. Finally, we break the feedback loop of the FDA and see what the phase margin is when the loop gain curve crosses the 0 dB region. At a phase margin of about 150 degrees, we can confirm that the FDA configuration is stable. The next area we will focus on is distortion. One way to quantify distortion products is by expanding their transfer functions into a power series. For an amplifier with a differential output, such as an FDA, we have two transfer functions for the generic expansion of the two outputs, which are equations 1 and 2 respectively. Here we can see that quadratic terms give rise to second-order harmonics, and cubic terms give rise to third-order harmonics, and so on. Taking the differential output of equation 1 and 2, we get equation 3. In a fully differential amplifier, the odd-order terms retain their polarity while the even-ordered terms always stay positive. When the differential output is taken, the even-order harmonics cancel. This means that FDAs do not introduce additional even-order harmonics. This distortion performance can be seen by comparing the THS 4551 and the OPA 625 datasheets. At a supply voltage of 5 volts, bandwidth of 100 kHz, gain of 1 for the THS 4551 and a gain of 2 for the OPA 625, and a load resistance of 1 kiloohm, we see that the THS 4551 has an HD2 and HD3 of minus 128 dBc and minus 139 dBc, while the OPA 625 has an HD2 and HD3 of minus 122 dBc and minus 140 dBc. In order to test the settling time, we need to see how long it takes the ADC's error voltage to settle within 1/2 LSB before the acquisition phase is over. Our driver should settle to about 19 microvolts in under 300 nanoseconds. Please watch Building the SAR ADC Simulation Model Precision Labs video linked below in order to correctly model the ADC. Once your model has been built and your ADC driver is added, you can test the settling time by going to Analysis, Transient, and running a transient analysis. For the discrete configuration, the time it takes the error signal to settle within 1/2 LSB is about 141 nanoseconds, which is under the ADC's acquisition time of 300 nanoseconds. Our final error voltage at 300 nanoseconds is 427 nanovolts. For the FDA configuration, the time it takes the error signal to settle within 1/2 LSB is about 206 nanoseconds, which is under the ADC's acquisition time. Our final error voltage at 300 nanoseconds is about 1.14 microvolts. In summary, there are two configurations we can utilize to convert a single-ended signal to a differential signal to drive a differential input ADC: 2 discrete amplifiers or 1 fully differential amplifier. In this example, we use the THS 4551 and 2 OPA 625. For noise, the OPA 625 with an added capacitor and the THS 4551 produced similar noise levels. The THS 4551 proved to be stable, while the OPA 625 proved to be marginally stable with the potential to need extra circuit alterations to make it stable. FDAs have the added benefit of reduced even-order harmonics, making the THD performance of the FDA better than the discrete amplifier. Both configurations settle under 300 nanoseconds. The discrete solution requires 2 amplifiers to be used, thus doubling the amount of quiescent current needed to run the amplifier. And finally, the FDA configuration only requires around 9 components, while the OPA 625 configuration requires around 16. That concludes this video. Thank you for watching.